The P-51 Mustang broke the Luftwaffe's back. America's pride, freedom's symbol. The fighter that saved Europe. But the textbooks lied to you. The man who designed it was born in Germany. Edgar Schmued, Hornbach, 1899. He served as a mechanic in the Austro-Hungarian Air Force during World War I, watching German warplanes take flight. Then he fled to America and built the weapon that would annihilate his homeland's Air Force. The engine that made it unstoppable? British. Rolls-Royce Merlin, the same power plant that drove the Spitfire. The idea to jam that British heart into the American body came from a British test pilot, Ronnie Harker, flying out of Hucknall, England. The supercharger that let it breathe at 30,000 feet? Designed by another British engineer, Stanley Hooker. The mass production that turned it into a war-winning machine? Detroit. Packard Motor Car Company built 55,000 engines, churning out British power under American efficiency. A German refugee designed the body. British engineers gave it the heart. American factories built it by the thousands. But this international miracle did not happen by choice. It happened because of desperation. 1940. London was burning, and Britain needed fighters immediately. The sky over the capital belonged to the Nazis. Wave after wave of Luftwaffe bombers hammered British cities while Messerschmitt fighters prowled above, hunting for prey. The Royal Air Force was holding the line, bleeding from 1,000 cuts, fighting a war of attrition it could not afford to lose. But the crisis was not what most people think. British factories were smashing production records, churning out Spitfires and Hurricanes around the clock. In June 1940 alone, 446 fighters rolled off assembly lines. By the end of the year, over 4,200 new aircraft would be built. The Harrogate program had transformed British industry into a fighter-producing machine, dispersing factories across the country to avoid destruction, setting quotas that seemed impossible and then exceeding them. The problem was not metal and engines. The problem was flesh and blood. Trained pilots were being lost faster than new ones could be trained. Every month, only 200 freshly qualified pilots emerged from training schools. Every month, combat chewed through far more than that. You could build a Spitfire in weeks, but you could not build a combat-ready fighter pilot in anything less than months. Aircraft sat on airfields, pristine and ready, with no one qualified to fly them into battle. Desperate times demanded desperate measures. The British Purchasing Commission boarded a ship to New York with a checkbook and a single question for every American aircraft manufacturer they could find. What can you sell us right now? Not next year, not in 6 months. Right now. They needed fighters, bombers, trainers, anything with wings and guns that could keep the Luftwaffe at bay until Britain could train enough pilots to match the German onslaught. They walked into North American aviation with a specific request. Build us the Curtiss P-40 Kitty Hawk under license. It was a solid aircraft, reliable, proven in combat. Not spectacular, but available. The British were not looking for miracles. They were looking for numbers. But when they sat down with Dutch Kindleberger, the company president, something unexpected happened. Kindleberger turned to his chief engineer, a quiet man with a thick accent and penetrating eyes. Edgar Schmued sat across from the British delegation, listening to their request for the P-40, and something flickered across his face. Not agreement, contempt. This was a man who had crawled through hell to reach this moment. After the First World War shattered Germany's economy, he had fled to Brazil in 1925, working for General Motors' aviation branch in São Paulo. 7 years of exile in South America, building engines in the tropical heat, dreaming of a future that seemed impossible. Then came 1931. Immigration quotas to the United States were brutally strict, a fortress wall against the desperate masses fleeing European chaos. Out of millions who applied, only 794 people received entry visas that year. Schmued was one of them. He had taught himself engineering in German factory apprenticeships, studying aviation in every spare moment, devouring technical manuals while other men drank and gambled. No formal degree, no university pedigree, just raw obsession and an understanding of aerodynamics that came from watching those early German warplanes struggle into the sky during the Great War. He knew what worked and what failed. He knew how German engineers thought, because he had been one of them. North American Aviation hired him in 1936 as a preliminary design engineer. He had worked on bombers, on export fighters for Peru, on projects that never saw production. Now the British were sitting in front of him, asking for the P-40, and Schmued could barely contain his disgust. That aircraft was obsolete, a relic. By the time it reached England, the Luftwaffe would blow it out of the sky without breaking a sweat. He had watched those German fighters evolve, knew their capabilities, understood their engineering philosophy. The P-40 was bringing a knife to a gunfight, and these desperate Britons were about to waste precious months building an aircraft that would get their pilots slaughtered. Kindleberger knew that look on Schmued's face. He had seen it before when his chief engineer encountered something that offended his engineering sensibilities. So he asked the question that would change the war. "Ed, do we want to build P-40s here?" Schmued had been waiting for this question. "Well, Dutch, don't let us build an obsolete airplane. Let's build a new one. We can design and build a better one." "It's obsolete," Schmued told the British delegation directly. "By the time it reaches England, the Germans will blow it out of the sky. Don't buy the P-40. Let me design something new, something aerodynamic, something that slices through the air like a knife." The British were furious. They did not have time for experiments. They needed planes now, not engineering fantasies. London was burning while this German immigrant pitched them dreams on paper. They gave him an ultimatum that sounded like a joke. 120 days. If the prototype is not rolling out of the hangar in 120 days, the deal is off. 120 days. 4 months to invent a fighter plane from scratch. Design, engineering, construction, testing. Most aircraft took years to develop. Schmued had 4 months. Kindleberger looked at his chief engineer. Schmued looked back. They accepted. 120 days. 4 months to invent a fighter plane from nothing. Schmued and his team worked around the clock. They slept under their desks when exhaustion finally won. Drafting tables covered with blueprints, calculations scrawled across blackboards, coffee cups piling up like ammunition casings. The clock was ticking, and every hour mattered. Schmued was obsessed with one thing: drag. He wanted the plane to be slippery, to cut through air with minimal resistance. Speed was life in aerial combat, and drag was the enemy of speed. He turned to radical new technology from NACA, the National Advisory Committee for Aeronautics, the laminar flow wing. Most aircraft wings were curved sharply on top to create lift, but that curve also created turbulence, and turbulence meant drag. NACA had been experimenting with a different approach, pushing the curve further back along the wing. It reduced turbulence. It reduced drag. On paper, it was revolutionary. Schmued adapted it for the Mustang. The wing would be thinner, sleeker, with the maximum thickness point moved back from the leading edge. Air would flow smoothly over the surface, instead of breaking into chaotic eddies. Less turbulence meant less drag. Less drag meant more speed. It had never been done on a production fighter before. NACA had the theory. Schmued was betting the entire project that theory would translate into reality. The design took shape. Clean lines, minimal protrusions, everything streamlined for speed. On paper, it looked like a masterpiece. But paper did not fly. Metal did. And the deadline was racing toward them like an oncoming train. September 9th, 1940. 102 days later. They beat the deadline by 3 weeks. The prototype rolled out of the hangar, gleaming silver in the California sun. NA-73X. It looked fast, just sitting on the tarmac. Sleek, aggressive, nothing like the blocky fighters of the era. Test pilot Vance Breese took it up for the first flight. The controls were smooth, responsive. The aircraft handled beautifully. Low-level performance was exceptional. North American had delivered exactly what Schmued promised: a clean, aerodynamic fighter built in record time. The British were impressed. They immediately ordered 320 aircraft. They gave it a name: Mustang. The RAF Mustang Mark I went into production, and by 1941, the first examples were shipping across the Atlantic. But there was a problem. A catastrophic problem that would not reveal itself until those Mustangs reached England, and British pilots took them into combat. The aircraft needed an engine, and the Americans had installed the Allison V1710. It was a good engine for a truck or a low-altitude attack plane, but it lacked one critical component: a two-stage supercharger. And that missing piece of technology was about to turn Schmued's masterpiece into a death trap. The Allison V1710 was a solid engine, reliable, powerful at low altitude, perfect for ground attack aircraft or anything flying below 10,000 feet. But it had a fatal flaw: no two-stage supercharger. A supercharger forces more air into the engine, compensating for the thin atmosphere at high altitude. The Allison had only a single-stage unit. Above 15,000 feet, it gasped for air like a drowning man. Power dropped off dramatically. The Mustang became sluggish, slow, vulnerable. In aerial warfare, altitude is everything. He who flies highest shoots first. He who controls the high ground controls the battle. The Luftwaffe understood this perfectly. German pilots in their Messerschmitt Bf-109s and Focke-Wulf 190s would simply climb to 20,000 feet and look down. They watched the Mustangs struggling below, engines wheezing in the thin air, unable to climb higher. Then they dove, attacked from above, and climbed back to safety. The Mustang could not follow, could not fight back, could not even run. The RAF test pilots were blunt in their assessments. Below 15,000 feet, the Mustang was magnificent, fast, maneuverable, a joy to fly. Above 15,000 feet, it was a coffin. And over Europe, combat happened at 20,000 feet and higher. The most advanced airframe in the world, Schmued's aerodynamic masterpiece, was being used as a glorified crop duster. The RAF was bitterly disappointed. They had a beautiful aerodynamic sports car with a broken engine. The Mustang was reassigned to Army cooperation duties, low-level reconnaissance, photographing enemy positions, shooting up trains, and supply convoys. Ground attack missions where altitude did not matter. It was humiliating work for an aircraft designed to dominate the skies. The most advanced airframe in the world, Schmued's revolutionary design with its laminar flow wing and sleek lines, was being used to strafe railway yards and take reconnaissance photos. A thoroughbred racehorse pulling a plow. The American military had even less interest. The U.S. Army Air Forces stuck with their P-47 Thunderbolts and P-38 Lightnings. They looked at the Mustang's high-altitude performance and dismissed it entirely. Schmued's creation, built in 102 days, was ignored by his adopted country. By 1942, the Mustang seemed destined for obscurity, a footnote in aviation history. A promising design ruined by the wrong engine. The British had hundreds of them sitting in squadrons, capable of incredible speed at low level, but worthless where the real air war was being fought. Then a British test pilot climbed into a Mustang cockpit at a small airfield in Hucknall, England, and everything changed. May 1942. Hucknall, England. A Rolls-Royce facility tucked away in Nottinghamshire. Ronnie Harker was a test pilot for Rolls-Royce, one of the best in Britain. He had flown everything from Spitfires to experimental bombers, knew engines and airframes the way a surgeon knows anatomy. The commanding officer at the Airfighting Development Unit invited him to try something different. An American fighter called the Mustang. Harker climbed into the cockpit and took it up. Immediately, he felt something special. The controls were beautifully balanced, responsive without being twitchy. The airframe was clean, slicing through the air with minimal drag. At low altitude, the aircraft was a dream to fly. He pushed it higher, 15,000 feet. The engine began to struggle, just as the reports had said. Power fading, performance dropping off. But Harker was not thinking about the engine. He was thinking about the airframe. He landed, climbed out, and walked straight to the Rolls-Royce engineers waiting nearby. What he said next would change the course of the air war. This airplane is not a failure. It's just holding its breath. Give it the right engine. Harker had seen the potential that everyone else had missed. The Mustang did not need to be redesigned. It did not need a new wing or a different fuselage. It just needed a proper power plant. And Harker knew exactly which engine could save it: the Rolls-Royce Merlin. Harker called his boss at Rolls-Royce. Ernest Hives, the man who had built the company into an engine empire, listened to the proposal. A Mustang with a Merlin engine. American body. British heart. Within 48 hours, Ray Dorey, head of the engine flight test section at Hucknall, was consulting with his engineering team. Could it be done? The Merlin was physically larger than the Allison. The cooling system would need redesigning. The engine mounts would have to be completely reworked. But the numbers looked promising. Hives picked up the phone and called Air Chief Marshal Wilfred Freeman, the Air Member for Production and Research. Freeman was one of the few men in the Air Ministry who understood both engineering and urgency. He listened, he agreed. May 13, 1942. A high-level meeting at the Ministry of Aircraft Production. The proposal was simple: convert 5 Mustang aircraft to Rolls-Royce Merlin engines as an experimental program. If it worked, it could give the RAF the high-altitude fighter it desperately needed. If it failed, they would have wasted 5 aircraft and a few months of engineering time. The ministry gave the green light. Rolls-Royce received authorization to proceed. 5 Mustangs would be pulled from RAF inventory and sent to Hucknall for conversion. The project had a name: Mustang X. But the engine that would transform it had been years in the making, designed by another British engineer who had revolutionized high-altitude flight. The key component already existed. Stanley Hooker had designed it a year earlier. Hooker was a Rolls-Royce engineer who specialized in one thing: superchargers. In 1938, he joined the company and immediately began revolutionizing how engines breathed at altitude. His breakthrough was the two-stage, two-speed supercharger for the Merlin 60 series. Two compressors instead of one, working in sequence. The first stage compressed incoming air, then the second stage compressed it again before feeding it into the engine. An intercooler between the stages kept temperatures manageable. The result was an engine that could breathe thin air at 30,000 feet as if it were sea-level oxygen. This was the technology that had saved the Spitfire. When the Focke-Wulf 190 appeared over Europe in 1941, it outperformed every British fighter at altitude. The Spitfire Mark III could not compete, but the Spitfire Mark IX, equipped with Hooker's Merlin 61 engine, could climb higher and fight harder. It turned the tables on the FW-190. Now the engineers at Hucknall looked at the Mustang sitting in their hangar. Then they looked at the Merlin 61 with Hooker's supercharger. The American airframe was better than the Spitfire in almost every way. Lower drag, longer range, cleaner design. It just needed the right engine. The idea seemed insane. Rip out the Allison, jam in a Merlin that was physically larger, redesign the cooling system, rework the engine mounts, and hope it all fit together. But if it worked, they were about to attempt engineering surgery that should not have been possible. June 1942. Hucknall. The Rolls-Royce engineering team began the operation. 4 Mustangs were selected for conversion. Serial numbers AL975, AM203, AM208, and AL963. They tore the noses off the aircraft, exposing the engine bays designed for the Allison 5 1710. Now they had to fit a 27-liter V12 Rolls-Royce Merlin into a space built for a smaller American engine. It did not fit. The Merlin was physically larger, heavier by 300 pounds, and the mounting points were completely different. Wiring had to be rerouted. Coolant pipes needed new pathways. The propeller shaft required modification. Engine formers had to be adapted. It was like trying to install a lion in a kennel built for a dog. The mechanics worked around the clock, cutting, welding, fabricating custom parts. The biggest challenge was not the size, it was the heat. The Merlin ran incredibly hot, especially the 2-stage supercharged version. It needed serious cooling, more than the Allison ever required. The Mustang had a distinctive design feature, a large scoop under the belly for the radiator. Schmued had designed it for the Allison's cooling needs. Would it work for the Merlin? Nobody knew for certain. If this failed, they would have destroyed 4 perfectly good aircraft for nothing. If it succeeded, they might just win the war. The first conversion, AL975, was fitted with a Merlin 65 engine and a 4-bladed Rotol propeller. The engineers made minimal modifications to the engine bay, keeping changes simple wherever possible. A smooth cowling covered the installation, with an additional chin radiator added beneath the nose. By October, it was ready. Time to see if the Frankenstein aircraft could actually fly. The biggest problem was not fitting the engine. It was managing the heat. The Merlin ran incredibly hot, especially with Hooker's 2-stage supercharger compressing air twice before feeding it to the cylinders. In the Spitfire, engineers placed radiators under the wings to handle cooling. But the Mustang had a completely different design. Schmued had built a large air scoop under the belly of the aircraft. He designed it to cool the Allison engine, but nobody knew if it could handle the Merlin's heat output. The engineers were taking a massive gamble. Then physics did something unexpected. Air entering the scoop flowed over the radiator, absorbing heat from the engine coolant. As the air heated up, it expanded. Hot air takes up more volume than cold air. Basic thermodynamics. If the exit duct was shaped correctly, that expanding hot air would accelerate as it escaped, creating thrust. This was called the Meredith Effect, named after the British engineer who first described it. Instead of the radiator creating drag and slowing the aircraft down, the waste heat actually generated forward thrust, a cooling system that pulled double duty as a miniature jet engine. Schmued had accidentally designed the perfect cooling setup for an engine he never intended to use. His scoop, built for the Allison, turned out to be ideal for the supercharged Merlin, but it needed Hooker's high-output engine to make the effect work properly. German engineering met British power, met American aerodynamics. The marriage was complete. Now they just had to see if it could fly. October 13, 1942. Hucknall Airfield. Captain R.T. Shepard, Rolls-Royce chief test pilot, strapped into the cockpit of Mustang X serial number AL975. He had flown hundreds of aircraft, tested every variant of the Merlin engine in service. This was different. This was unproven, untested, a hybrid that existed nowhere else in the world. He fired the starter. The sound was completely different from the Allison-powered Mustang. The old engine had chugged and rattled. The Merlin growled, a deep, guttural roar that shook the ground beneath the aircraft. 12 cylinders of British engineering thundering to life inside an American airframe. Shepard pushed the throttle forward. The Mustang X leaped off the runway, climbing faster than any Mustang had a right to climb. He pulled back on the stick, gaining altitude rapidly. 15,000 feet. This was where the old Mustang started wheezing, where the Allison engine gasped for air, and performance died. Shepard passed through 15,000 feet. The Merlin kept pulling. No hesitation, no power loss. 20,000 feet. Still pulling strong. The supercharger doing exactly what Hooker designed it to do, forcing compressed air into the cylinders, compensating for the thin atmosphere. 25,000 feet. Shepard was now in Luftwaffe territory, the altitude where German fighters dominated. The Merlin was still producing full power. He leveled out at 30,000 feet and opened the throttle completely. The old Allison-powered Mustang topped out at 390 miles per hour. This Frankenstein hybrid, this marriage of American body and British engine, hit 433 miles per hour. The absolute ceiling tested at 40,600 feet. Shepard landed, climbed out of the cockpit, and delivered his assessment to the waiting engineers. They should not build another airplane. They should just build this one. But there was a massive problem. Rolls-Royce could barely produce enough Merlins for the Spitfires, Lancasters, and Mosquitoes already in service. They could not supply the American military as well. The solution would come from an unexpected place: Detroit. The test results were stunning. The British wanted to convert hundreds of Mustangs to Merlin power immediately. But there was a nightmare logistics problem. Rolls-Royce was already stretched to breaking point. Every factory running at maximum capacity, producing Merlins for Spitfires, Lancaster bombers, Halifax bombers, and Mosquitoes. They could not supply the American military on top of British demand. Production was maxed out. The solution came from across the Atlantic. The Merlin blueprints were sent to Detroit, to the Packard Motor Car Company. This is where the Axis lost the war. Not on battlefields, but in factories. Packard had been a luxury car manufacturer, but they understood mass production at a scale Rolls-Royce could not match. The contract was signed in September 1940. Packard would build Merlins under license, with Rolls-Royce maintaining strict control over every aspect of production. The engineering challenges were substantial. British drawings used first-angle projection. American drawings used third-angle projection. Every blueprint had to be redrawn to American standards. But Packard kept the British threads, the British fittings, the British specifications. Rolls-Royce engineers supervised the entire process, ensuring quality control remained absolute. Packard even had to manufacture their own thread-cutting tools because they were using British thread standards instead of American SAE threads. It was a massive undertaking. By August 1941, the first Packard-built Merlin engine ran. Designated V1650-1 for American use, Merlin 28 when supplied to the RAF. Production ramped up fast. By the end of the war, Packard had built 55,523 Merlin engines. The P-51B was born. American body designed by a German refugee. British engine with a British supercharger. Mass-produced in Detroit under British supervision. 3 nations, 1 weapon. But it arrived just in time, because over Germany, a slaughter was happening. 1943. The U.S. 8th Air Force was attempting to bomb Germany into submission through daylight raids. Strategic bombing, hitting factories, refineries, infrastructure. Break the Nazi war machine from the inside. But the bomber crews were dying. The B-17 Flying Fortresses were tough aircraft, bristling with defensive guns, capable of absorbing tremendous damage. But they were slow, flying at altitudes where German fighters excelled, and they needed escorts. The problem was range. The P-47 Thunderbolts and Spitfires escorting the bombers had short legs. They could fly to the German border, maybe slightly beyond. Then fuel gauges dropped into the red, and they had to turn back. The moment those fighters turned around, heading home to England, the Luftwaffe struck. German fighters had been waiting, watching, conserving fuel and ammunition. They let the escorts leave. Then they swarmed the undefended bombers like vultures on a carcass. October 1943. One week that became known as Black Week. The Americans lost 148 bombers in 7 days. 1,500 men gone, shot down, captured, or dead over Germany. The generals halted the deep penetration raids. The losses were unsustainable. Entire squadrons wiped out. Crews that made it back traumatized, talking about watching their friends' aircraft explode. Burning men falling through the sky. The bombing campaign was failing. They needed a miracle. They needed a fighter that could fly all the way to Berlin, fight the Luftwaffe at altitude, and still have enough fuel to make it home. The P-51B Mustang with its Packard-built Merlin was about to answer that prayer. The 8th Air Force generals looked at the new P-51B Mustang specs. They studied the fuel consumption figures. They did not believe them. "Check it again," one general ordered. The numbers came back the same. Schmued had added internal fuel tanks behind the pilot in the fuselage. It was a dangerous design choice. If those tanks were hit by enemy fire, the pilot was sitting on a bomb. But it gave the aircraft incredible internal fuel capacity. Add external drop tanks under the wings, disposable fuel cells that could be jettisoned when empty or when combat started, and the range became astronomical. 1,600 miles. The P-51B could fly 1,600 miles on a single tank of fuel. That meant flying from England to Berlin, fighting for 15 minutes over the target, and still having enough fuel to make it home. No other single-engine fighter in the world could do this. The P-47 maxed out around 800 miles with drop tanks. The P-38 Lightning had better range but struggled at high altitude where the Luftwaffe operated. The Spitfire was a short-range interceptor, brilliant in a dogfight but useless for escort duty deep into Germany. The Mustang could go anywhere the bombers went, and with the Merlin engine, it could fight the Luftwaffe at any altitude. The first P-51Bs arrived in England in November 1943. The 354th Fighter Group received them first, technically part of the 9th Air Force, but immediately co-opted by the 8th for escort missions. March 1944. The bombers launched again, this time with a different kind of protection. The Luftwaffe was about to get a very unpleasant surprise. March 1944. The bomber formations launched again, heading deep into Germany. German radar operators spotted the massive formations crossing the coast. Hundreds of aircraft, B-17 and B-24s, flying in tight boxes for mutual defensive fire. The Luftwaffe scrambled every available fighter. This would be another slaughter, another turkey shoot once the escorts turned back. The German pilots climbed to intercept altitude, 25,000 feet, watching the bomber stream push deeper into German airspace. They waited for the inevitable moment when the American fighters would peel away, fuel exhausted, leaving the bombers defenseless. But the fighters kept coming, deeper into Germany than any escort had flown before. The German pilots were confused. Those had to be short-range aircraft, P-47s or Spitfires that had made a navigation error. They would run out of fuel soon, forced to turn back or crash. Then the American fighters dropped their external fuel tanks, silver cylinders tumbling away, falling toward the ground far below. The aircraft pivoted, turning to engage. The German pilots froze. They recognized that silhouette, the distinctive scoop under the belly, the laminar flow wing, the clean lines. Not a Spitfire, not a Thunderbolt. Mustangs. Over Berlin. The aircraft they had dismissed as a low-altitude reconnaissance plane was now hunting them at 25,000 feet, deep in the heart of Germany, with fuel to spare. The Luftwaffe had nowhere left to hide. The hunters had become the hunted. The Americans did not just escort the bombers anymore. They went hunting. By mid-1944, the P-51 Mustang had done what no other aircraft could do. It broke the Luftwaffe. German fighter pilots were demoralized. They knew that no matter how high they climbed or how deep they hid inside Germany, the Silver Ghosts would find them. The skies belonged to America now. The Mustang pilots received new orders, terrifying orders. Go down to the deck and destroy everything that moves. The targets were not aircraft anymore. The targets were logistics. German rail networks, supply convoys, river barges, bridges, anything that kept the Nazi war machine running. The P-51 was armed with 6 Browning M250 caliber machine guns, 3 in each wing. When fired together, they did not punch holes. They tore metal apart. A 3-second burst dropped 13 pounds of ordnance downrange. Locomotives exploded. Freight cars shredded. Trucks disintegrated, flying at 400 miles per hour at treetop level. One mistake, one telephone wire, one lucky shot from a soldier with a rifle, and it was over. But it worked. Gun camera footage from 1944 shows train after train erupting in clouds of steam and smoke. Supply convoys shattered on French roads. Barges sinking in German rivers. The Nazi logistics network was being systematically destroyed. By D-Day, the German army was paralyzed. They could not move armored divisions because the Mustangs were watching. German train drivers refused to work during daylight hours. They only moved at night, hoping the darkness would protect them. But the war was not over yet. The Nazis had one final card to play. A technological leap that made every propeller-driven fighter in the world obsolete overnight. The Nazis played their final card, the Messerschmitt Me-262, the world's first operational jet fighter. No propeller. 2 Junkers Jumo turbojets slung under swept wings. top speed, 540 miles per hour, 100 miles per hour faster than the Mustang. When P-51 pilots first encountered it, they were stunned. The aircraft looked like it came from the future. It screamed past them before they could even get their gun sights on target. No propeller wash, no engine roar, just a howling turbine shriek, and then it was gone. The Me-262 was armed with 4 30mm cannons. A single burst could tear a B-17 in half. German pilots called it the Schwalbe, the swallow. Allied pilots called it a nightmare. The P-51, king of the skies for barely a year, was suddenly obsolete. In a straight fight at altitude, the jet won every time. Faster, deadlier, untouchable. If Germany had deployed the Me-262 earlier, in larger numbers, the air war might have turned. But by late 1944, it was too little, too late. The Luftwaffe was crippled, fuel was scarce, and experienced pilots were dead or captured. The Mustang pilots could not outrun the jet. They could not outclimb it. They could not dogfight it. But they could outsmart it. The Mustang pilots had what German technology lacked: numbers and cunning. They studied the Me-262, looking for weaknesses. Every aircraft has vulnerabilities, even a jet from the future. They found it. The jet was fast in the air, untouchable once it reached speed. But it was slow and vulnerable during takeoff and landing. The turbojets needed time to spool up. The aircraft could not accelerate quickly from a standstill. And when coming in to land, gear down, flaps extended, it was just as slow as any propeller fighter. The Mustang pilots developed a brutal tactic: rat catching. They stopped trying to fight the jets in the air. Instead, they loitered over German airfields, orbiting at altitude like vultures, waiting. When a Me-262 approached to land, gear down, speed bleeding off, the Mustangs dove. It was not a dogfight, it was an execution. The German pilots were helpless. They could not accelerate away. They could not maneuver hard without stalling. They were locked into the landing approach, committed, vulnerable. Gun camera footage shows Me-262S exploding on final approach, tumbling into the ground in fireballs of burning jet fuel. Others were caught during takeoff, still accelerating, not yet fast enough to escape. Among the American pilots was Chuck Yeager, a fighter ace who would later become the first man to break the sound barrier. In November 1944, he shot down an Me-262. He proved that a piston engine fighter could still defeat a jet if the pilot was smart enough to exploit the situation. The Mustang held the line until the very end. May 1945. Germany surrendered.